Good afternoon, ladies and gentlemen. It's my honor today to be invited here to give you a sharing about a guide for selecting an ADCS for your satellite mission. And what is the objective of engineers? And here, the engineers, I'm referring to the people who are working for the satellite owners, that the company who own the satellite and they have to build the satellite and operate the satellites. So I believe their first priority is to extract value from these satellites. So these engineers should be focused on the payload and how to utilize the satellite buses to get the payloads to have its optimal performance. So this comes to an important question that I think many people are mentioning and explaining for it, is about how to determining the pointing requirements for your mission, because this is very important to get the best use of your payload. So criteria including like the pointing knowledge of your individual components, such as star tracker, or the pointing knowledge of your whole ADCS. So here are a little bit different, because like if you have a star tracker, and while this star tracker is installing on your integrated ADCS or your self-built ADCS, there will be some misalignments of these components. So usually the pointing knowledge of your ADCS will be lower than the component level. And then while you are installing this integrated ADCS into your spacecraft, there will be another misalignment. So the overall pointing knowledge of the spacecraft will be lower. And if you are installing a payload onto this spacecraft, and then the pointing knowledge or the pointing accuracy of this payload will be lower. So these are things users should be keep in mind while you're making your criteria. And then there are absolute pointing accuracy and relative pointing accuracy, where the relative one is usually referring to the jitter. So people are maybe less familiar with the relative pointing accuracy. So actually this is a drift of attitude defined by a period of time. For example, like 30 seconds or like 1 milliseconds, depending on the user's application. So usually we have a scenario that's optical payloads that are taking images to the Earth. So these image or these cameras, they have exposure time to capture the image. So if the satellite's attitude is shaking while taking images, then their resolution will be of the image will be some degradations. So while you are building a remote sensing satellite, the relative pointing accuracy is a very important criteria. And there are also slew rates, that how fast can your ADCS to change the angular velocity of your satellite. So let's break down to different types of satellites. So there are the remote sensing satellites. If you have a narrow field of view, then the absolute pointing accuracy will be very important, because if your satellite is drift too much away from your targeted object, then your target object will be out of your the field of view of your camera. And there are communication satellites. Usually they require less sophisticated ADCS, because their pointing requirements are usually lower than the remote sensing satellites. So for example, if you are using a UHF antenna, and usually these antennas are omnidirectional, so you didn't need to have a good pointing requirement. And so even if you are installing expand antenna on your satellite, and then if you have 4 degrees of angular deviation, then they only cost 0.1 dB of losses for the antennas. And the higher the communication frequency you are using, and usually this antenna requires requires a better pointing accuracy. But for most of the CubeSat satellite mission, people may use a S-band antenna or X-band antenna. So usually you maybe don't need a pointing accuracy that's better than or 1 degree or 0.1 degree. And if your CubeSat has something like a deployable antenna, and you should be watching that if these ADCS should be able to provide a maneuver to let the solar panels to capture the sun. So after knowing the pointing requirement of a mission, here comes to several different methodologies of building an ADCS. So traditionally, people used to design and build manufacturing every component from ground, and then to integrate their whole system. So this is the old days, the space agency driven days that people cannot find available vendors from market. So they build everything from ground. And then since the space industry becoming more and more mature, and then the dividends of labors are getting more and more professional. So there are some vendors provide a commercial out-of-shelf components, so people can pick up the reliable components and integrate their own ADCS. And according to our investigation, that most of the CubeSats are built by the second methodologies nowadays. But there are also another trend is popping up that people started to purchase integrate ADCS, which the vendors help the people to integrate everything all together from the components, and then help them develop the firmware, the algorithms, and then also the calibration. So the users does not require to build the ADCS everything by themselves. And I believe this is a trend for the market, because everything's are getting more and more professional. And then there are also always the fourth method that you can always hire a contractor to build your satellites. And these contractor could purchase components or purchase an integrated ADCS and build an ADCS for you. But today's talk, I will be focused on method 2 and method 3 majorly. So if you are adopting methodology 2, that you are buying components and then integrate your own ADCS, there are a couple of things you should be aware of, including when you are picking up a reaction wheels. There are some specifications that are other than the angular momentum or the torque. These are the magnetic disturbances specification, and also the imbalance of the rotor, which is the major contributor of jitter. And then when you are choosing your attitude sensors, especially you are choosing the image-based one like Star Tracker, and then they usually have a lower update rate. So these sensors usually limits your bandwidth of your control system. And if you wanted to have a better update rate, then your power consumption will get larger. And so while you are implementing your own ADCS, there are system errors that quite often occurs for these self ADCS builders, because when you are trying to align the different component frames, even you are using locating pins, and then the sensor will have some deviation or misalignment while installation. So this causes the degradation of your overall performance. And also there are the nature of the components. There are random errors for these attitude sensors. And then if you are implementing the algorithm by yourself, and then there might be some human error that your algorithm may have some blind spots, or may behave not the way you think it will be in space. So it's important to have a software in the loop simulation, and then also a hardware in the loop simulation. But both of these two methods is hard to validate the relative pointing accuracy. So it requires people to take efforts to get the things to be done with a reliable way. So here's the introduction of the pros and cons of using an integrated ADCS. That's they are usually more expensive then you purchase the individual component and integrate the system by yourself. But of course, there are also benefits because you don't have to develop the algorithms by yourself and do a calibration, and then it saves you manpowers. So, but if you count in these equipment costs or the manpower cost and time cost, in fact, maybe integrated ADCS would be a more reliable and economical choices for you. And here I divide the ADCS into three categories by its pointing accuracy. And there are purely talker-based ADCS. They are just around 10 degrees of pointing accuracy. And then there are a reaction wheel based, but without star tracker. And the one with star tracker, which is the most expensive and the most sophisticated one. And these the different ADCS are different by their cost, of course. So finally, I would like to introduce you with several findings that are observed on the trend of this ADCS industry. There are some companies are developing the system identification methodologies to determine the mass properties information on orbit using their developed software. And then there are Agile satellites that are utilizing CMGs, control moment gyros, to have a better slew rate compared to traditional solutions. And then better components always driving the technology to go further. So there are attitude sensors with a higher update rate. And then here I'm going to introduce you with Tensor Tech's unique offer, a control moment gyro that is based on a spherical motor. So this spherical motor-based CMG is comparatively smaller than the traditional CMG because they utilize a multi-axis actuator, which can provide people with a smaller volume weight with the compared to the traditional solution, which is the one you see in the picture here. So yeah, this is my presentation today, and thanks for your listening.